Hello, good evening students. In last class we have discussed the problems on main dimensions of induction motor. Today we have to discuss the design of stator winding. So number one, we have to see design of stator winding. So it is already well known fact that the induction motor has main three parts. Number one, stator. Number two, rotor. Number three, air gap. So we have to see design of these three aspects. In this stator winding, we are using single layer winding. This winding can be used for low rating motors up to 5 HP. If the rating of motor is increased, then we have to go for double layer winding. So how we have to design the stator turns per phase? It is already known that specific magnetic loading B average equal to P pi divided by pi dl, where P is number of poles, D is diameter, L is length of stator core. Hence, from this expression, we have to calculate the flux per pole. Now we can see phi equal to phi m, that is flux per pole equal to maximum flux. So we are getting the expression for phi m. So another factor, we have to calculate the number of stator turns, Ts. For this, we have to consider stator phase voltage. Stator phase voltage ES equal to 4.44 kWs F phi m into T. It is similar to the induced EMF of transformer expression except kWs. So what do you mean by kWs? kWs is stator winding factor, where T is the number of turns. So number two, length of mean turn. So it is also another important calculation. As per voltage less than 650 volts, the empirical formula is given to calculate the length of mean turn of stator, that is LMTS equal to 2 times of L, 2.3 tau plus 0.24, where tau is known as pole pitch, tau equal to pi d by P. Next one, design of stator conductor. So already we know that we are having stator and rotor, respective winding. Winding used in stator, it is referred as stator winding or stator conductor. For calculation of this, it is already known that kVA rating of three-phase machine Q equal to 3 times of phase voltage, phase current into 10 to the power of minus 3. That is 3 times of ES, IS into 10 to the power of minus 3, because we are taking stator into considerations. So where ES is stator phase voltage, IS is stator phase current. From this expression, it is possible to calculate stator current. So Q, it should be converted into volt ampere, then 3 times of ES, that is Q for phase, ES stator voltage for phase. This stator voltage depends on again type of connections, whether the stator winding is star connected, whether the stator winding is delta connected. So ES equal to EL in case of delta, ES equal to EL by root 3 in case of star. This design mainly depends upon winding connections. So after calculation of IS, we have to assume the respective value of current density in the stator winding. In standard assumption, this value varies between 3 to 5 amperes per millimeter square. After assuming the current density, then it is very easily possible to calculate the cross-sectional area of stator conductor. That should be equal to current per current density. So AS we are getting in millimeter square because current density is in millimeter square. So if round conductors are used, then again this area of conductor may be equal to pi d square by 4, where d is the diameter of stator conductor, where AS is the cross-sectional area of stator conductor, it is in millimeter square. Hence, it is possible to design diameter of stator conductor. Then next we have to see design of stator core. The design of stator core mainly consists of design of teeth, then depth of stator core and number of stator slots. So one important fact we have to remember, the stator core is made of laminated structure to reduce the eddy current loss or to reduce the heating effect. Next we have to see stator slots. Another important aspect, the choice of stator slots will affect on the performance of motor. It may be winding problem, either it may be magnetizing current, either it may be insulation. Mainly we are having two types of slots, one open type of slot, another one semi-enclosed type of slots. You can observe the diagram. Now from the diagram you can clearly observe open type of slots and semi-enclosed type of slots. Open type of slots means the width of slot must be same at opening at bottom. You can observe the diagram. Width of slot must be same at any height of the slot. Either it may be opening W0 equal to WS from the diagram, where W0 is width of slot at opening, WS width of slot, DS depth of slot. You can observe from the figure there is a one slot between two teeths. Two teeths. Teeths means projected part. Slots means it is a cavity. It is a space available for accommodation of windings. From the diagram you can observe there are four conductors. There are four conductors are placed in one slot. We are having mainly two types of slots, open slot and semi-enclosed slots. What are the advantages in open slots? Already we know that width of slot must be same at any instant or any height of the slot, that is W0 equal to WS. Such slots are called open slots. What is the advantage? It is very easy to replace the individual coils. When the coils are damaged, when the coils may be burnt, so to replacement is very easy. Number 2, it reduces the slot leakage. Hence, it reduces the total leakage of the leakage reactance of the machine. Hence, it improves the performance of machine. Number 2, semi-enclosed type of slots. So, width of slot at the opening is less. The width of slot at the bottom of the slot is more. These coils are placed in the slots first after insulation should be provided. The coils are placed in the slot very first. After that placing we have to provide the insulation. Next advantage, it provides less air gap contraction factor. It also results the smaller value of magnetizing current. It is very clearly observed that less value of magnetizing current, which results higher value of power factor. This is very important phenomenon for design of energy efficient machines. So always you have to reduce the magnetizing current. Hence it is possible to increase the power factor of the machine. Then it also provides low tooth pulsation loss and less noise. It is also another important parameter for industry. If motors operates with less noise, these are more optional selection. Hence almost all type of induction motors are designed with semi-enclosed type slots. Now we can observe from both diagrams. In figure 1 you observe very clearly there is a tapered teeth. Teeth is parallel. Teeth is parallel sided where the slot is tapered. Such type of arrangements are used in design of low rating induction motors, whereas figure number 2 represents parallel sided slot with tapered teeth arrangement. Such type of arrangements are useful in design of medium size and large size of the induction machines. Choice of stator slots. So the choice of stator slots will affect the following factors. Number 1, tooth pulsation loss, leakage reactance, ventilation, magnetizing current in terms of power factor, iron loss and economical. Hence, choice of stator slots should keep these points into mind. By keeping these points into mind, there is some rules we have to follow. Hence, the slots per pole per face should be an integer. Before that, the slot pitch should lie between 15 mm to 25 mm. So we know that stator slot pitch YSS equal to gap surface divided by total number of slots. Gap surface is pi d, total number of stator slots SS. Next we have to see design of total stator conductors must be equal to number of phase into conductors per phase. Number of phase is 3, conductors per phase is ZS. One conductor equal to 2 turns, it becomes 6 TS, where TS is stator turns per phase. Hence, conductors per slot equal to total stator conductors divided by total number of stator slots. It must be equal to 6 times of TS divided by SS. Guidelines for selecting of stator slots. Already we have discussed one point. The slot pitch should satisfy from 15 mm to 25 mm. So by using this relation, you have to calculate number of stator slots when YSS equal to 25 mm, and again you calculate number of stator slots when YSS equal to 15 mm. Hence, it gives the range variation of stator slots from minimum number to maximum number. Step number 1. Step number 2. The stator slots should be a multiple of Q. Where Q is slots per pole per phase. Hence, you have to calculate for typical values of Q. Q equal to 2, Q equal to 3, Q equal to 4. You go on calculation. So stator slots equal to number of phases into number of poles into slots per pole per phase. It is very easy. What is Q? Slots per pole per phase. What are the dividing factors? You multiply. Dividing factor is 1, pole, multiply. Dividing factor is phase, multiply. Hence 3 times P into Q. Step number 3. You list the number of stator slots satisfying step number 1 and step number 2. If number 4, if slot loading is given, then stator slots should also satisfy the slot loading. Slot loading equal to IZ, current through the conductor, into ZSS, number of conductors in one slot. Slot loading, what are the number of conductors in one slot? What is the amount of current flowing? This gives slot loading. Last step is also very important. If one value is available, step number 1, step number 2, step number 3, step number 4, that is the final value of stator slot. If 2 possibilities are available, that means stator slots, 2 conditions are satisfying up to step number 4, then what is your final judgment? That means we have to select lower number of stator slots for economical design. If we are designing lower values of slots, then winding material required is less. It ultimately creates economical design. You remember, this is also one of important fact. You have to mention very clearly, for economical design I am going to select lower values of stator slots. It is my decision. You write there, then you proceed. Thank you, sir, to one and all.